our guests to join, our can start for just let's give it like another 5 minutes to just quickly check in on Paul. And yeah, hi Paul. I didn't know that you were here already. Okay. Yes. Since Paul is here, I'll just start. Hello. Okay. So Paul is here. I guess I can just start. Welcome again, everybody, to this fun technical session. I hope we enjoyed the last week's office hour. And then today we have another wonderful session by Paul. And I'll just quickly go through the ground rules so that we don't take much time and Paul can have as much time as possible to himself. Again, let's respect each and every one of us in the session and create a welcoming and supporting environment for all of ourselves. Please keep your microphones muted unless you want to speak and you've been asked to talk. Make sure that there are no background noise. Engage actively by sharing your thoughts, because we'd love to hear from you. We'd love to hear your opinion. Let's speak one after the other. Raise up your hand. When it's your turn, you'll be allowed to speak and the call to speak. Let's keep whole conversation focused on machine learning, AI, and all of the topics that we're talking about. Let's not spam the chat box with links that that are not relevant to the community. We've joined on time. Let's make sure we wait up until the end of the session so that we can get the maximum value of the event. Again, drop your questions in the chat box, even if we're not at the time or the segment of questionnaires, we will take it and make sure we take it. Even if we run out of time, we'll take it and send it to the community. Most importantly, let's have fun and let's learn from one another. So I'll just quickly go over today's session. We're going to have a welcome session, which we're having the main session after welcoming Paul, and then the Q&A, and then we wrap up with announcements. So I'll just quickly go through Paul's bio. Today we're going to be talking about Beyond the Buzz, how neural network actually works. Or actually learn, is going to be taken by Paul Asali. Paul is a software engineer who is focused on system designs, embedded systems, and AI, with expertise ranging from command inline tools to edge AI application. Paul builds robust technical solutions for complex problems. He is the founder of FlashCon Africa, and is currently engineering the architect for a localized service marketplace startup. So without further ado, I'll just allow Paul to take it on from here. Paul, we're ready. We believe that you're ready, and I'll just stop sharing so that you can stop sharing. Welcome again, Paul, and thank you for honoring our invitation for this session.
Hi, am I audible? Can you hear me?
Yes, I can hear you. I'm sure the other person can.
Okay, thank you very much for honoring me. As I don't know what your name is, but ML Lagos has said, my name is Paul, and I'm happy to be here. Really excited about this topic. It's one that I find very interesting, and I just feel like it's not really talked about enough, because in the vast amounts of solutions that AI adjacent and have come out in the past couple of years in a very short amount of time, to be honest, because if you think about the past 5 years, it's almost as if we're in a renaissance period where there's almost every year there's new innovation. Every year or every couple of months you hear that there's a new model that's come out, new architecture that's come out, and it surpasses like the previous ones, right? And we're moving so fast that not only are we moving so fast, but we're moving so fast and people are adapting so fast to these new technologies that it's almost as if we're leaving the fundamentals behind. And I think that's still really important. And to stand out as much as possible in maybe the job market, or yeah, I guess the job market, and to really be able to contribute in a meaningful way to what we have out there. I think it's very important if to understand the fundamentals of how these systems, how these things happen, because a lot of people just know Chat GPT, but like, how did that come about? And your first interaction with AI, I bet, was probably someone telling you that, um, hey, have you heard about this new website that you can just go and type something in and it gives you the answers? But and ever since then you've just been using it, right? And for a lot of people it's that way, but it could be more. And it's good to be inquisitive about things that we use in our day-to-day, or just things that surround us. And that's how you become enlightened, and that's how the world moves forward. People that are the frontiers of this are the inquisitive ones. So that's my pre-introduction to today's session and why it is important. And you can see it's well reflected in the title of today's topic, Beyond the Buzzwords. So beyond all the chat GPT, the model, all that kind of fancy talk, beyond your Google Colab notebooks and all that stuff, and the chips, the hardware, that you just select from a drop down. Beyond all of that, what actually happens behind in your network? What is in your network? How many of us have heard? Oh, Shay, I'm so sorry. Pleasure to meet you, Shay. How many of us have heard what? And I'm going to share my screen in a minute. To accompany my yapping, there's going to be a lot of yapping in today's session. How many of us have heard of what? Sorry, I've heard the phrase AI is a black box. Well, not AI. Well, maybe AI or neural networks are a black box. If you've heard that, can you just do a show of hands? And I'm sharing my screen now. Please let me know if you can see it. Is it one person that's sharing? Sorry. Is my screen visible?
Yes.
Okay, good. Two hands are up. It's only two people have heard that phrase. If you, yeah, it's good. Three. Okay, that sounds good. If you watch the series, the popular series, comedy slash sci-fi series, Silicon Valley, there's a part there where the CEO, the guy, the three musketeers of code, made something and they're trying to figure it out, and they dropped that word, that phrase, AI is, well, not a phrase, a sentence. AI is kind of a black box, and to some extent it's quite true, but there's another part of it just being that people don't really understand what goes behind, like what's happening there, and just say it either ways without actually knowing what exactly goes on and why it is called a black box. And today we're going to try and demystify that. So yeah, this is my slide. I'm not going to do the play. Should I do that? Because it looks weird. Anyways, so I'm going to go in an immersive view, and please at any point in time, if I stop, if you can no longer hear me or you can no longer see my screen, please let me know. So yeah, we'll start with the components of neural networks. So, and we'll try and like explain some of the justifications for the structure that he has and where all of this, began. So our goal today is to open that black box, visualize how layers are connected, and we'll see some code implementation of these fundamental ideas. The journey that we're about to embark on starts with a very essential building block, the perceptron. How many of us are familiar with that term? Have you heard of the term perceptron before? I want it to be interactive actually. I don't want to be the only one talking. Is that fine? Shay? Okay.
Yes,
All
it's
right.
for
Who wants to volunteer to say something about what the perceptron is? Okay, nobody wants to. All right, so a perceptron, the journey started with this idea called a perceptron, right? And this was started by a guy called Rosenblatt back in 1984. Let me check my notes. I need to be sure. Yeah, 1958. Sorry, this is why it's important to have notes. Rosenblatt was a psychologist and a researcher at that, which is very interesting that all of this started from somebody that wasn't, into this world wouldn't really be considered a tech bro or someone like that. But again, it boils down to the fundamental principle of being inquisitive about the world that you live in. So Rosenblatt, it was one such person and spent a lot of time researching about the human mind, the brain, how it works. You might have heard that till today, the most complex thing to study is the brain. And we don't really know much about how the brain works. But yeah, they were mapping that out and thinking about how the brain works at a fundamental level. If you're not a science student, then this might come as news. Your brain is made up of very tiny cells called neurons, and these neurons are all connected. There's possibly trillions. I don't know how many there are, but like countless number of these neurons work together to make decisions and to move your arm and do all this fancy stuff that the human body is capable of doing. And he looked at that and thought of a way to solve problems using the same idea founded in nature, in the human brain, in a neuron, to solve real problems, computational problems, decision making, if I may. And at this point, I'm going to switch my screen to a much more immersive um, whiteboard, not a whiteboard, yeah, a board that I made, presentation, just so that we can really explore what this perceptron is all about. Again, this might be, oh, thank you very much for that. Human brain contains approximately 86 billion neurons. Yep. And then there's all the connections as well. Also, it's like layered. So it's 6 billion neurons, and each one has like connections with every other one. You can see how many connections you can get. So yeah, at this point, I'm going to switch my screen to another tab. It's an Excalibur tab, and this is where we sort of delve into the idea that Rosenblatt brought about. Think about what exactly perceptron is and how it relates to this idea of making decisions or solving problems. So, I'm going to start by motivating this as this topic here: perceptron as a decision-making apparatus. And that's pretty much what well, a simplified dumbed down way of thinking about what a perceptron is it's a decision making apparatus. It's something you use to make a decision. And to make this make sense, I made an example. So say you want to go to the movies, but you're going to the movie in your mind is going to be determined by three important variables: the weather, whether or not you're going to have a company, or, and when I say company, I mean someone will accompany you to the theater, and how far away the movie theater is. So those are the three variables. And don't yet get scared. We're not talking about XYZ just yet, even though there is inside of this. But when I say variable, I just mean they can change. And to be honest, in maths, that's what it means. It just means something can change. So we have those three data points in our head. We know that weather is going to determine whether or not we'll go. Company, whether I'm going to have someone that will go with me or not, and how far this theater is. But for someone like me that's an introvert, it doesn't even really matter what all of this is. I will end up not going likely. And we'll see how that makes sense, because you see this bias here is exactly what I just said. A bias is what you put into a perception to say, I want the outcome to be biased towards this general direction. So if I, as an introvert, I could put a bias here that makes sure that regardless of what these conditions are, the output is probably going to be in favor. Also, all of these things come together as numbers, because in reality, we cannot take those abstract concepts and program them. We need to represent them somehow, and math is the way to represent the unseen. So, and I hate to be sounding very um, mystical here, but I couldn't find a better word. But math is the way that you relate those real world concepts into programming, into computing. So here, if you think about it, yeah, sorry, before I forget. Then now this, out of these three variables, whether that's if it's going to rain or not, if you have a company, and the proximity, those three variables can also be weighted. So if you see the notes that I put here, let me zoom in. I'm hoping the notes are quite clear. Weights signify importance. So for you or for a person, the weather might be the most important part of this. And if we're being realistic, it probably is for everybody, because if it's raining, you can't go out anyways. So it's more important than having someone to go with you, because even if you have someone to go with you, the weather is bad, you probably wouldn't want to put that person through the stress of going in the rain with you anyways, and you yourself would probably wouldn't want to go out. Then also how far it is. So these two variables are less important than weather. Well, for some people, at least. Some people might not care about that. And maybe for them, it's regardless of what happens. If I have a company, then I will go regardless. So the weights are a way to signify to a perceptron that some variables are much more important than others. So if we assume that weather is the most important one, it follows that weather would carry more weight by virtue of it being the most important one. Meanwhile, company and proximity probably share the same level of importance, at least for this example. And I can assign some arbitrary value to these variables, or at least to the weights of these variables, to say for weather, it's going to have an importance score of 4. For company, it's going to have an importance score of 2. Proximity is going to have the same because they have the same level of importance. So think of weights as importance levels, and the numbers that we associate with them as just arbitrary values that represent how important it is. In the grand scheme of things, these numbers could be anything. It only matters when we think of them relative to one another. So as such, you hear people say a lot that the weights are just of relative importance, relative size. So whether is big compared to company and proximity. But we know in general that 4 is just a regular number. This could be anything. But for the purpose of this example, I just put 4. And company and proximity, they share the same value because they have the same level of importance. Any questions so far? Before I continue. All right, I assume there are no questions. The bias, which is this third component, and now this is again, let's keep this structure in mind. This is the general structure of a perceptron that Rosenblatt proposed, because we look at what a neuron looks like. It looks like this. It's like input signal, which are electrical signals in your brain, and there's output signals that the neuron sends out. And you think of that in terms of the signals that the neuron will send out to the next neuron. And we'll look at how that relates to the structure that Rosenblatt also brought about. So we have the input signals. We have an additional one, bias, which sort of gives us, the programmer or the owner of the decision, some control, like I said earlier, to bias the general outcome of it. So let's say in this case, we want to make sure that our output is biased in the direction of making sure that whatever output we get favors weather. So a bias is supplied to force the perceptron to be more amenable to a preferred outcome. So if you prefer that this perceptron, this neuron, this virtual neuron, should only tell us yes or no, given that weather is in a favorable condition and at least one other of the two variables is in a favorable condition, then we'll add a bias number that helps us to reach that kind of outcome. And we'll see how this makes more sense in the next section. When we're actually putting in those numbers, you see how that actually makes sense. The third component of our system, of our perceptron, is the outcome. Yes or no, in this case. It could be of a different kind. You could have maybe 3 outputs. Not necessarily 3 outputs, but like 3 possible potential outcomes, right? But in general, your perceptron gives one output. So this was the general structure that Rosenblatt proposed, and it very closely mirrors how a neuron works. And now let's move on to another way of thinking about a perceptron as a linear classifier. And when I say linear classifier, I mean generally that this is just something that will give you one selection out of a field, or out of a set of potential answers. So it's one answer you are getting out of a set of potential answers. So in most cases, though, it's usually 2, at least for the conventional, for the traditional definition of a perceptron. It's a set of potentially 2 answers, yes or no. So if most of the definitions of a perceptron usually involves the perceptron giving you an outcome of either a true or a false. Now, the logic that we've acquired from this first section, it carries over into the same place. We're just looking at it from different perspectives. So we've seen how a perceptron can help us to make a choice. So as a decision-making apparatus, giving some variables and a bias, it will give you an outcome. So think of the bias and the variables and the weighted variables as constraints for the perceptron to give you an outcome. Now, what exactly is the perceptron doing? And this is where it starts to make even more sense when we start to think of it as a mathematical function. That's what a linear classifier is. It's practically a mathematical function that takes in input, gives you an output. In this particular case, it's all it is doing is just a summation. It's just adding up these numbers together. So we have these 3 inputs, and I've shortened them into W, C, and P. So our inputs, whether or not company, which stands for whether or not we have company, and proximity, P. So WCP. And each one has its own weight, W1, W2, W3. Remember, the weights are just numbers that indicate how important an input is compared to the other ones. So we have those weights, those weighted inputs, and it all goes into our neuron alongside a bias, and then it gives us an output. The same exact structure as decision-making POV. In this case, we can also think of our input values for weather, company, and proximity. Because earlier, we were introduced to the idea of weights, which are just numbers that depict how important a variable is. But the variable itself should have a value if it's to make sense for a mathematical function. So we can think of this as binary inputs. So a 1 for our weather variable just means the weather is good. If it is a 0, we can think of it as the weather is bad. So in this case, I'm saying the weather is good. I'm saying also here that company, I have no company, so nobody's going to accompany me, so that's 0. I'm also saying that this proximity, by setting proximity to 1, I'm also saying that it is close, it's not too far off. And of course, we have our weights. Again, weights just signify importance, relative importance. Now, if we look at the bias of this value, we set it to a number like -7. This particular bias, by the way, is one such that it guarantees that when we compute, when the neuron does its calculation or whatever it is doing, it will be such that it will only give an output of true if, remember our bias condition, if the weather is favorable and at least one other variable is favorable. Favorable being one other of company and proximity is set to a 1. So output is only going to be 1 if company or proximity is set to a 1. And let's look at what exactly that would look like if the neuron is to take all of these inputs and like compute it. It looks something like this. It's literally just addition. So it's not doing anything fancy. And this is why you notice that a lot of times when you see a diagram of a perceptron of a neuron, they'll just put a summation sign in the middle because it's literally just doing addition. It's adding all those weighted sums together alongside this bias and then making a decision, giving you an output of this is what I calculated, giving these inputs and your order of importance, your weighted importance, plus your bias. This is the output. That translates to some meaning to the programmer or whoever it is that modeled the neuron to begin with. Given these values, in this particular case, we said that the weather is favorable and the weight of the weather is 4. So what we do, or what the neuron does, it multiplies that value together to create a weighted number for the weather. So that's just 4 times 1 is 4. Then it adds that value to the company's weighted sum. Again, it's just what is the weight of company, how important is company? It is 2. It has 2 points for importance. The current company value is telling us that it is 0, meaning that we don't have anybody to go with us. So that's 2 times 0. Plus, it is not too far away. That's why proximity is set to 1. 2 times 1 is 2. In total, the output, I'm going to call this, let's represent me with Z, is 6. So we've gotten a number. What then are we to do with this number? And how does our bias help us to get close? Help us to get to that output that we're looking for. This is where it's important for us to, before we finalize on this, it's important for us to think of something called an activation function. So the structure of a perceptron as it pertains to the output is such that it doesn't just give you the output as the sum that you've calculated. It actually passes through something called an activation function. And the activation function maps your calculation to the output space. Remember, our output space in this condition, in this case, is that we only want a yes or a no. What does 6 mean in this case? It means absolutely nothing. Is this a yes or is this a no? All I'm seeing on my screen is numbers. I'm just adding numbers together. And I'm sure most of us have the same disposition as well, because like, what's all this math that you're seeing? How do you map 6 to the output of yes or no? And for a typical perceptron, this is where something called the activation function comes in. Your activation function takes as input the calculation from the neuron. So the output from this big round neuron goes into the activation function. And that's why you see that this thing here, I put this f of z, which represents that the z, which is our addition, goes into this function f, the activation function. And there are multiple different functions that you can use. But for in Rosenberg's paper, he specified a step function. And a step function, let me just do a quick reminder or a quick math primer. A step function in math is just a function that gives you an output of 1 Actually, this line that I drew here might be confusing. Let me quickly remove that. By the way, any questions so far? I'm guessing.
There's a couple of questions in the chat.
Oh, I haven't been looking at that. So sorry. Is the bias separated to the data variables? Not sure I understand the question. Another question is this one shot encoded? What do you mean? You guys can omit and ask the questions to make it make sense to me.
Yes, sir, please. I just wanted to understand the sense of bias in this case.
Mm-hmm. Yeah, so
The-
a bias. Carry on.
Oh, okay. Did you get it?
Yeah, okay, yeah, I did. I got the question. So a bias is another number, and it will make sense in a minute. It will make more sense in a minute. I'm going to use this example to help you see why a bias is important. So a bias is just another number that we pass into the neuron to effect a change in the output, to bias or shift the output towards the preferred outcome. So if we want the outcome to be that, given all these inputs, the output should always be yes, if and only if weather is favorable, and at least one other of these two is favorable. We'll put an appropriate bias there, and you very soon now the maths is this is all just maths, to be honest. We'll put an appropriate bias, which is just another number that gears that output, all of this towards the favorable output that we want. And it will make more sense in a minute. Once I'm done with explaining the step function part, we'll look at what the equation looks like and then see how the bias affects our summation. Because all of this is just going to get added up to a given output. So the other question says this one shot encoded. I don't get what that means. And
Yeah,
someone may. Oh, okay.
I was going to ask the question. Yeah, so you were having those weather values and company as actual numbers. Then we suddenly switched to binary. Was that just one hot encoding, or was that moving to one hot encoding at that point?
Mm-hmm. Yeah. So actually, in many cases, it can be binary like this, especially when you are dealing with encoded information like pixel data. So for things like a basic image classifier, like an image perceptron, or you're building a convolutional neural network from scratch, you find that data a lot is binarized, but it doesn't have to be. This is just so that it makes sense to us, because if we don't use whether it's true or false, then it will have to be fuzzy values dealing with fuzzy data. So, and that complicates the problem further. This is a simple approach to understanding how a perceptron deals with the information that it gets. So it's intentional, yes, but you don't need to overthink it just yet. Someone said, "Thank God I studied engineering." Well, I'm hoping that even for those that did not do any STEM, I'm hoping that I'm explaining it in a way that makes sense to you. But of course, if you have questions, I'll be happy to answer them. So yeah, just want to quickly explain what the step function does. You see these values here, this line. This just tells us that anytime the function gets a number that is greater than or equal to 1, it will always give you a 1. So this line is our x-axis. So it starts from 0 to infinity. From 1 downwards, well, not necessarily 1, from anything greater than 0 downwards to the right of 0, our value is always 1. But if it's to the left of 0 or from 0 downwards, the value is 0. That's all the step function does. So if you pass in a value like 2 to the step function, it will give you 1. If you pass in a 0, it will give you 0. If you pass in 0.5, it will give you 1 because it's greater than 0. If you pass in a negative number, the step function will give you 0. It's a very simple function, right? So if you think about it, our output here of 6, to make it make sense to us to binarize it as an output of either 1 or 0. And in programming, in computing, a 1 or a 0 is the same as true or false, where exactly in the same way that I've used it here, where a 1 is true, a 0 is false. That's all we need from our perceptron. We need it to tell us, is it a 1, should I go or should I not go? And in this case, we have an output of 6. Then to make that normalized, we pass it through an activation function. Activation function is synonymous to the activation in your neuron when your neuron is firing based off the input that it gets. So what is the thing that activates the function, or the thing that activates the perceptron, is the activation function. It determines whether or not it gives a 0 or it gives a 1 output. So if you look at the notes that I put here, f of 6 is 1, since if we give our step function a number that's greater than 0, it always gives us a 1, and 6 gives us is a number that's greater than 0 and gives us a 1. This is what goes on inside of the neuron. Now, if we think back to what we said earlier of the bias, you notice even here, we didn't do anything with our bias. All we did was just add the numbers up, right? Now let's see how the bias affects the change. So given this particular set of inputs, when we summed it up, or if we speak about it in regular terms, we're saying if the weather is good and I have no company and I have a theater that's close by, I should be able to go to the movie theater. According to the perceptron, is telling us based off this math that we've done, this addition we've done, and our step function has stepped in. If you caught that joke, I stepped in and normalized the output to a 1. It's saying that given this, no bias, by the way, we haven't considered the bias, we should be able to go out. But our bias is set to -7 intentionally for cases like this, because I'm biased to saying I only want to go out if the weather is good and I have at least one other good thing going on out of these two variables, right? So you have 0, we have a 1 here, and we have our company to be 0, and we also have a proximity to be 1. So at least one of the two variables that we have here is good, and also the weather is good. That means that, and by the way, we should also be adding bias, which is why I said earlier that we're not doing anything with bias. So let's look at what that looks like when we add in our bias to our equation. So this would change into 4 multiplied by 1. We also would have 2 by 0, 2 by 1, and a bias of -7. Right? So what does that give us? So before we had, this is 4, 2. So that gives us a number -1. So I've set my bias such that it gives us this output of -1. And when we pass this into our activation function, who can tell what the output would be? What would be the output?
0.
Yeah, 0. A 0 telling us that we can't go out, even though our variables are all lined up, and our intention is to go out, given that weather is good and proximity is good, and either one of these company of proximity is good as well. What this means is that I've chosen a horrible bias number, because now my bias is telling, because of my bias, I've overstepped. It's telling me that I can't go out even though conditions are in place. So what would be a good bias number here? A number like -5 would be good, or -4. If we change this to -4, what output do we get? So we have 6 minus 4, that gives us 2. Our activation would then be f of 2. What would be the outcome in this case? What does the perceptron tell us to do here?
1.
A 1 or a true, exactly. So this is how we use a bias number. So we're selecting a good bias number, and this is how all of it comes together to give you an outcome. When we're looking at a perceptron as a linear classifier, and it's linear and classifier in the sense that it gives you a class of one of 2 options, a true or a false. You notice that when we tried f of -1, we got a 0. If you change the weights of the parameters, the weights or the bias of your neuron, your output is always going to be one of 2 values, a 0 or a 1, because of our step function here. And this is a good justification for how a step function is structured, especially when you think of it in terms of the activation function. Before I proceed, do you have any questions? Let me check the chat. Yeah, 0, 1. So bias can be seen as it's just another variable that you add into it to push your desired outcome. Okay, great. At this point, we're going to take a detour back into our fancy slide. At least I hope that now we understand what a perceptron is at a fundamental level. The journey started, like I said earlier, with Rosenblatt and his structure of the neuron. As a matter of fact, if we go deep enough, we'll find that this way of reasoning about problems, and I don't want you to think about the perceptron just yet as it relates to a neural net just yet. We'll talk about that, but think of perceptrons as a universal generic concept or a generic way of approaching problems, of thinking about problems. Because did you know, for example, that a perceptron, or a NAND gate rather, is a kind of a perceptron? What does NAND gate have to do with machine learning and ML, you ask? It's because perceptrons are a generic concept and they apply to many different things. So let's just go back before I start rambling on and on. Let's go back to our slide to guide the conversation that we're having. How much time do I have left? Just a 1 hour thing.
Not so much, actually.
What did you? Yeah. Time
I
is
said
over.
not so much, actually. No, it's not over. Well, I think you have about 13 minutes more.
Yikes. Okay. All right. So yeah, this is the building block of what we're talking about. The perceptron is building block of, and hopefully this diagram makes more sense to you now. You see the sum function, which is everything we're doing. We're taking the inputs, adding it to the bias, and then passing that into our activation function, and that gives us an output. Hopefully, in the past 30 minutes, I've been able to make this make sense to you. So if you read any materials or source, this should make reasonable sense to you. The next part of this presentation will now focus on how this concept was now applied to solve even much more complex problems, and how that birthed the idea of neural networks. Yeah, exactly. Scaling up from perceptron to neural networks. A neural network that's why it's called a network. The neural is because a perceptron is modeled after a neuron, so there go, it should in fact call a neural network. Each and every one of these circles you see here are perceptrons. And a neural network is structured into three layers. There are hidden layers, which are the ones in the middle here. These are actual perceptrons, like we saw in the previous presentation. These are our perceptrons. The input layer doesn't really comprise of actual perceptrons. These are just normalized data inputs, and these data inputs are sent they're passed into the actual neurons. The neurons process them, pass them up. Their outputs go into yet another layer of perceptrons or neurons. Perceptron is a mouthful. So not really a mouthful. It's just it has a lot of syllables. I have to say perceptron. That's 3 syllables. Neuron is like 2, so it's easier to say neuron. That's why you find that a lot of the time people just say neuron. So yeah, but they mean the perceptron for sure. So I might use that interchangeably as we go. And then here, these are also neurons at the end, and they are the ones that will give you your output. In this case, who can take a wild guess? How many outputs does this particular neural network give? What?
2.
2, yeah, exactly. It gives 2 because there's 2 outputs neurons here. And this, pardon me, this thing says yes, no. This is quite misleading. It should, in fact, it depends on what you have there, what this particular neural network is doing. So if it's going to be a single output, you would have a single output neuron here. So this gives 2 outputs. And there are many different ways you can justify having a neural network that looks like this, right? So yes, the major points here: strength in numbers, the hidden layers, and I think I've explained why it looks like this. Always remember that the input layer usually doesn't have any neuron in it. It's just input data that has been normalized to fit through the neural network. The problem with neural networks, though, is that in order for them to be good, they have to learn. And I'm going to try and justify this by going back to where we're coming from real quick to our slide on perceptron, the one we had before. So I'm going to go back there and let's talk a bit more about our step function and as it relates to perceptron. So remember, our step function is what takes our garbage summation, whatever we get, probably wouldn't make any sense because we're trying to make a decision and we're getting 10, 6, 2. Those are not numbers that directly translate to a decision. It's just a number in our head. But if we have a mnemonic for understanding that kind of logic, like binary encoding, like the other person said, we understand, for example, that when we see a 1, it means true. And we see a 0, it means false. If we have that kind of mental framework, we can use that to justify the output that we get. And that works well for a basic perceptron and for other simple applications. But the problem that we're trying to now solve going further, and if you take a course on neural networks or deep learning, you hear that they probably would say something about how the anticipation, the enthusiasm that people had for neural network, it was high. It's like a it's like a sinusoidal graph if you graphed it over time, because at some point people were excited about it, then the excitement drops because of the problems that they had along the way. But newer and newer innovations just kept solving those problems, and up until where we are right now. So one such problem was like, how do you use this? How do you make this better? How does this, in a sense, learn? And when we think of neural networks, you hear that you are training your AI, and usually what is happening is at first the weights that we have here, because you need to ask the question of how do you know what numbers to put here to begin with in order to get a favorable outcome. In this case, it can be easily manipulated. You can start with a very mathematical guess. But in large-scale systems like ChatGPT, large language models, and all those fancy ones in convolutional neural network, how do you know which weights you put here to make sure that when you put a 3 in front of it, it can tell you that this is in fact a 3? This is you don't know. You don't know beforehand at least. And that's where something called gradient descent and backpropagation is very important. But before we get there, we need to understand that the way it works is when you pass in, because you don't know beforehand and you need to figure it out as you go, what typically happens is we start our network with randomized weights. So we put rubbish values like I just literally did here. 4 to random weights and random, what's it called? Bias. That's what they call parameters, by the way. So when you hear a model has 5 billion, 10 billion parameters, means it has literally billions of weights biases. We start that way and then we try and figure it out as we go. The thing though is, because it's called learning, we already know what the right answer is as human beings. We're the ones training the AI, right? We already know what the actual right answer is. So what we do is we ask the AI to compensate by using something called a cost function. But it's very important to know what then happens when we tweak changes to our weight. So if we change the weight of W3 by a little, I need to be able to check how it is affecting the outcome. So let's say if you change W3, and obviously when we say change W3, it could be in the direction of increasing W3 or decreasing W3. That's the way it goes. It's plus or minus. I need to be able to say that if I increase W3, then the output will change in this direction. But we know from this that our step function only has 2 potential outputs, either a 1 or a 0. There's no way to say if you change W3 by increasing it, the output will increase by a certain percent. No, it's not. It's just going to either stay at 0, stay at 1, or just jump all of a sudden from 0 to 1. And you saw the example we had here. The moment we moved from -7 to -4, it was a night and day difference in the output. It just went from 0 to 1 immediately. That's a problem, because the goal is to be able to figure out how it is that we need to adjust this weight such that the the output is getting closer and closer to our goal. The step function is bad for this because it is too discretized. It's just 0 or 1. It's not smooth enough to know what happens when you change it, because the output is just wrapped inside, give me a 0 or a 1, give me a true or a false. To combat this, they came up with the idea of using another activation function called a sigma function. It looks like this. As you see, it is more smooth, meaning that it allows for values between 0 and 1. You can have 0 point something, 1 point something. It caps at 1, but it's a much more, it has more, it's smoother in general, and it's best for what we need it to do. Hopefully that makes sense. And so I'm going to go back because we don't have much time to this slide. So yeah, the solution to what I was saying earlier is using a sigma function like that, and that helps us to calculate the changes. So when we need to know how to adjust our weight, do we want to increase the weight or decrease the weight? And we do that by taking the gradient of that sigma function, of that slopey graph that you saw just now. So when we check that, we can use that to determine in what direction we need to adjust our weight. And that's what gradient descent is. It's about finding the local minima, not the local, but the global minimum of your cost function. The cost function, by the way, is what you graph to figure out how far away or how off your current neural network is, how smart it is. So if you've given it the first randomized weight and it gives you an initial guess, it's probably be rubbish. Your cost function is a function that that pictures how off or how badly performing your neural network is. You then take that and figure out what's the direction I need to go on my graph to get the global minimum. The minimum point being the point where your function is most closest to the output, the desired output. And I'm rushing through this because we don't have enough time. Actually, 1 hour is not enough to talk about all these things. So there's also
So you can take
Wait,
your
my time is
time.
up.
Oh, no, take your time. Just continue.
okay.
Yeah.
Yeah, so that's how gradient descent works. So usually we're trying to figure out, do we go and increase our weights, or do we go and decrease our weights when it comes to gradient descent? And there's something else called stochastic gradient descent, and it's a way to just batch apply all the directions in which we want to go to our weights or our network of weights, or in the neural network. And so propagation is the algorithm that you use to actually move the changes throughout the entire network. It's called there's propagation in there because we use that to propagate backwards from the output that we've gotten through the entire neural network. So it goes in a backward direction. So what happens usually is that when you determine and again, this comes out like as a matrix of values. So you usually just have a matrix of values here because you have 3 weights to adjust in this particular simple case. And then this one, on the other hand, has 6 different weights to adjust per perceptron. So you go backwards that way and then figure out how to adjust the weights in relation to the inputs of the perceptron, if that makes any sense. But yeah, either ways, as you see in this case, it says pass the blame backward layer by layer. So this perceptron is saying, hey, I was just told that I should increase my weight. What do you guys need to do to make sure that that happens from here? Because it is getting its own input weights from input x1 and input x2. So it comes here, says increase, that is propagated backwards until you reach the root layer, and then the actual change is applied here. There's some math involved, chain rule. I won't be able to obviously go into that, but I'm just going to show a quick example of what that looks like when we're talking, specifically of a perceptron. And it's just a way to, an interesting way, I would say, to demonstrate this idea of having a neural network predict something, be wrong, and then you calculate the cost, and then you adjust it based on how far off it is from the actual truth. So yeah, so it's like someone said, it's like shedding raw rice until you get the quantity that will be enough to cook for 2 people. That's a very interesting analogy, but yeah, I guess you can think about it that way. You just keep it's iterative, so it's like a cycle of for each step in your iteration, and that's what you see most times. If you are training a model on like Google Colab, you see it will tell you running through 100, whatever it is you set it to in your code, running through 100 epochs. Each epoch is a process of learning, it's applying backpropagation. It is calculating the cost at each stage. How far away is it from the actual right answers? And then it is compensating using gradient descent. So it calculates that cost function. It looks for the slope of the function and then checks, is it far away, should I increase the weight, or should I decrease the weight to get closer and closer to the most minimum point until it can no longer decrease or calculate any difference between what it is saying or the output it is giving and the actual output that is expected. So at this junction, I'm going to share my screen, and I'm going to try and quickly explain the code that I've put up. I've got, all right, a simple model for a perceptron. Can you see my VS Code screen? I should probably put this on a GitHub gist. Is it just, can you see my screen?
Yes.
Okay. So I think I explained why the sigmoid is a better. Yeah, I did. So this is just the sigmoid function, and it's expressed as 1 over 1 plus exponential raised to the negative z power. So the z, remember, the z is just the summation that you get from your perceptron. So when you add those three things together, whether the weighted sum of whether, company, and proximity plus your bias together, you get a z value. In this case, I call it, it's just the x input. And this is our activation function. So to give us an output, that's the answer basically. The output from your perceptron is your sigmoid. And the derivative of that is what we then use to calculate the gradient, because gradient is just dy dx, is the derivative, the rate of change. So it tells us how far off we are from the actual output of the function. This helps us to get that. And what we have here is our perceptron, or at least an imitation of a perceptron. And in here, it's very, very simple. So this particular perceptron, by the way, is what I'm going to try and do here. I'm going to try and train it to behave like an AND gate. And remember, an AND gate is one that if it has two inputs, if its two inputs are 1, then it's give you an output of 1. All other possible permutations will always give you a 0. So if you have a 0, 0, 0, 1, it will give you a 0. This is our sample data set, and these are our labels or sample outputs. So we're saying for 0, 0, output is, pardon me, 0. For 0, 1, output is 0. For 1, 0, 0. The only time we have a 1 for AND gate is a 1. And this is our input data set. You can imagine it looks like this. And for our perceptron, we're saying that it takes in 2 inputs. Obviously, we can change the input size to whatever it is we want. So we say it takes in 2 inputs. Then we set some random bias. You see that it is random here as well. So we set a random bias, and we put this learning rate here. For now, for the purpose of this, and we just ignore that for now because it's another rabbit hole to drill. And then we'll look at what's going on when we are doing our training. So our training here is really just forcing the neuron to use this input that we've set to figure out and give us a guess of, what do you think the output is going to be if you are giving 0, 0, 0, 1, 1, 0, 1, 1. And, as you see here, the prediction is wrong. It's just a rubbish outcome. And by the way, this is where we pass in the inputs. We add them up, as you can see here. And then we pass that into our sigmoid function to flatten the output for us as either a 0 or a 1. Or at least an approximate representation of a 0 or 1. Usually that's because the output will typically be something like 0.99, 0.98, 0.95, very, very close to it. And that's a consequence of using the sigmoid function, because it's a smooth function that doesn't just give you a 0 or a 1. It's to give you something in between. But closer it is to the 1, approximately 1, is what we're talking about here. So we make a prediction. Then this is where we're talking about we calculate the cost by looking at the actual label, which is either a 0 or a 1 based off what we have here, right? And then we look at the prediction that it's given. We look at that, we get the absolute value of that, and then we scale that up using we scale our derivative using the error that we calculated. So how far off is it from that prediction? The right answer, rather, how far off is it from the actual label? You know, and that's what we're doing here with this calculation. So we've gotten that difference, but it needs to make sense. For us to apply the gradient descent, we need to calculate the gradient as well, because it's then that we'll be able to do backpropagation on the network. Although in this particular case, this is just a single perceptron, right? So this is the quote unquote our makeshift backpropagation. You notice that we're adjusting the weight, and this is inside the for loop, by the way. We're adjusting the weight based off the learning rate, the gradient, and the inputs that we have. So we adjust that weight by doing a plus equals. And this is safe because if it's negative, it will add up and obviously decreases. If it's not, it will just be an additive operation. And we do the same thing for the bias as well. So we do this for a couple epochs. So in my particular case, I think I set it to 5,000, during training. But well, first of all, we need to see how well this model performs when I run it by itself. So we're not going to train it just yet. Or rather, let me comment this out. So I'm going to train just here. We're going to print out the untrained predictions. Remember, the goal for this thing is to tell us, is to give us the behavior of an AND gate. So for all these inputs here, the output should literally look like this: 0, 0, 0, 1. So let's run it and see what it actually does for us. I think turn up, yeah. Oh, I didn't save, sorry. Yeah, so for input 0, 0, it tells us that, oh, you might not be seeing my screen well. Sorry about that. I just remembered. So it tells us that this 0, 0 is practically a 1. So it's telling us that the output for this should be a 1. For 0, 1, it also says it should be a 1 because 0.6, you can round it up to 1. It's just 1 all through. So obviously garbage numbers. And it's also not consistent because if I run it a second time, you see that it gives, oh, wait, it is. That's weird. Okay, well, yeah, because we haven't changed the weight. That does make sense. Sorry about that. But yes, the point is that it will give you rubbish information if you don't train it. Now, if we train it, we call model.train, and then we run it this time around. Because I'm commenting comments. We run it this time around with our training, after our training, and again, notice that it ran through a couple trainings. This is 4,000, 5,000 epochs. This is epoch 1, 5,000 cycles, by the way, and we ran through all of it. It's a testament to how good or how fast it is your computers are, by the way. Segue, but again, back to the point. So we've seen that it has gone through the training, and we are seeing the error rates for each training. This is how far off it is from the actual values, the actual answers that we're looking for. But now the trained predictions show that 0, 0 is 0.0. This is practically 0. 0, 1 also 0. 1, 0 also 0. But for the one that we need it to be, actually 1, like an AND gate, it shows you 0.9, which is you can round that up to get 1. So this is a simple, I wouldn't say easy, but a simple way to visualize and think of the fundamentals of neural networks and how they actually work by the way, this is all the kind of this maths, all these things. These are the fancy stuff that PyTorch and TensorFlow. These are the kind of stuff that they do in the background for you, and all the maths. And it's all abstracted, and you can just call some methods, some functions, and it does all of that for you. But obviously, because even at the layer where we are operating these days with AI, there's a lot to even do. So why bother with the very involving parts like this, right? So yeah, I guess that brings me to the end of my yapping session. Thank you very much. I'm sure it's probably been quite confusing, but I think if you think of this as a primer that you can then build on top of, so if you go and read up, watch videos, and just practice, I guess you be able to have that grasp on the fundamentals even more. Any questions?
Thank you. Yeah, thank you so much, Paul. Guys, questions? Let's. Do we have any questions for Paul before we wrap this up? Okay, Martins, please ask your question.
Good evening.
Evening,
Good evening. So my question is not really about the lecture that was delivered. Anyway, Paul, thanks a lot. It was a great
Yeah,
session.
thank you.
Yeah. So I just recently started learning machine learning, and I've been searching different posts on LinkedIn, especially for deep learning. And I've realized that a lot of the, let me say, the interest of we Nigerians have been, or maybe it's my field, I mean, my LinkedIn field, it has been majorly medical imaging.
I can't really
Eh?
hear you, Michael. It's breaking. I think. Is it just me?
No, not just you. It's
What
network.
about now? How about now?
Oh, let's give it a try.
Oh. Can you hear me now?
Yeah,
Just
but
continue, Michael. We'll let you know.
Okay, okay, so this is what I'm saying. I think from my LinkedIn feed, right, I've been seeing a lot of the Nigerian deep learning focus on medical imaging. So here's my question. Is this due to data availability or there are other things that needs to be considered that speaking most of our research focused on medical imaging? That's my question. Thank you.
not sure. Did you hear that, Shay?
Not very clearly.
Do you mind
Can
typing
you
it?
Can you type your question, please, Michael?
Sure. Thank you very much.
Really sorry about that. Okay, there's some questions in here. How would you save the training model in this case? So in this case, you wouldn't be able to save it. The reason is that I did not build this using a framework like PyTorch or TensorFlow, which if you know anything about frameworks, they are very opinionated and teach you. So there's an entire the ecosystem for ML as it relates to what is vis-a-vis my deep learning and all these fancy models is it usually comes in form of this .pt files and those other blobs that store things like weights. So it's very intentional. They built it up that way so that you can easily share. And it's because of the necessity of being able to share things like weights from pre-trained models. It's built in a very tight way that mandates that if you are building using TensorFlow or PyTorch, you will be able to save your models as actual architects that you can share, upload to a cloud, and easily deploy them for ease of use. But if you're doing outside of that, you need to figure out a way to transfer your model represents. So because a model, when we're talking about a model, in this case, a neural network, it boils down to the weight. Every other thing can be imitated and constructed in whatever different environment exists. So ChatGPT will be practically just a zip file of weights and random weird files, .pt files and blobs that you can upload to another machine, and it's just running and spin and start working like exactly as that model. So it just boils down to knowing what the weights and biases are, the parameters. That's why they always say those things about billion number parameters and stuff, and how it costs them so much money to train. But once you train it, and once you have that inside of that framework environment, you're good. But because we wrote this directly from VS Code, there's no way to do that. So you can't save it in the conventional way. I hope that answered your question, Kinechiku. Thank you very much. I don't know how to pronounce your name. Let me, Alex. I would say Alex. Let me butcher that. The annoying, interesting POV in ML makes one wonder how those libraries are built. Yeah, I don't know about annoying, but yeah, you are very much right. They are very complex. To be honest, because it's not just one person that worked on it. So yeah, and so some of these are open source, and this is why understanding the fundamentals, and this is why I felt so inspired to talk about this. People don't realize the insane amount of engineering that happens behind the scenes. You just use all these fancy APIs, video tools, but there is an incredible amount of work that's been put into it, and I think it's worth spending time learning, because again, like I said at the very beginning of this thing, it's maybe the thing that separates you from another person, because everybody knows how to hook applications together. But in this very crazy job market, this might be the thing that makes you stand out, understanding the fundamentals. Okay, Martin, I finally got your question. You recently started learning deep learning, took some time to check recent works, and frequency of work focused on medical imaging. Is this due to pardon me, I'm reading the question. My question is this data availability or right? So you're asking because of how frequent the work is focused on medical imaging, is it due to data availability or are there other limitations? That is a very interesting question. I'm not sure I have a good way to answer it. It may be because of that, but I like to think that people have some form of motivation for the kind of work that they do, and maybe they're motivated by some problem in the medical space that exists. So maybe it's because of that. I'm not aware of any. I don't have enough information to answer your question. I'm so sorry in the way that would make sense. So, but I can only just give a guess. See, it's probably related to the problems that exist in the medical space. Did I get your question? Am I off topic?
While we wait for Michael, can you get the next question, please?
Right. Are there recommended materials, books for a deeper dive? Absolutely. How do I make my slides AI? Which is ironic because I'm talking about the fundamentals of AI, but AI actually makes slides. Yeah, I use Gemini a lot. But this particular slide, I'm very fascinated by as well. I don't know if I can if it's public. Let me try this link if it works. But it's a tool called GenSpark, and I only had to give it again, prompting is very important if you're working in it. So you need to be as specific as possible to get the best results. So don't be lazy with your prompting. So prompt well and structure your prompts well. So yeah, I gave a really structured prompt and it gave that wonderful output. I did not even have to send in a second prompt. I just took it the way it was and works with it. How did you dive into sorry? Yeah, how did you make your slide? Okay, I've answered that. Are there recommended materials? Yes, I absolutely recommend. God, H Factor, don't mind me. I absolutely recommend. What's it called? This dude, 3 Blue 1 Brown, from YouTube. There's a wonderful playlist that he has on fundamentals of 3 Blue. I'm typing that 1 Brown. Just check his playlist on neural networks. There's also another one I will send it to either Shay or Ifino so that they can send that.
Just send it to the email trail and also the slide. We wouldn't mind if you can share the slide, because right now it says no permission.
Okay. Yeah, I'll figure that out and get that across to you.
All right. Thank you so much.
Thank you for having me. I hope.
Yeah, thank you so much for we appreciate you, and then thank you for coming around.
Yeah, it was great to be here. Thank you.
So, let's just quickly do this. Please follow us on social media, that is Twitter and LinkedIn. And our upcoming events for the month of March, the technical sessions and the office hours, and also we're going to be having our International Women's Day event. The full communication will be sent out on the community group and on our social media. So that's why you should follow us and then join the community group if you aren't in the group. Yeah. So thank you. I know that we've gone way past our usual time, but we can all tell that this session was very, very informative and insightful. And I love what Paul said about how a lot of people are building on AI, but we do not know the fundamentals. I mean, it's a very important part of the market. I'll make link.
I think your network is bad.
Thank you.
So just okay, bye.